For centuries, we believed that black holes were the ultimate cosmic vacuum cleaners, devouring everything that came too close and holding it prisoner forever. Light, matter, entire stars, once they crossed that invisible boundary called the event horizon, they were gone, vanished, lost to the universe for eternity. The laws of physics seemed crystal clear on this point. Einstein's equations painted black holes as perfect prisons with no possibility of escape. But the story becomes extraordinary. In 1974, a young physicist named Stephen Hawking was working on what seemed like a simple problem. He wanted to prove that black holes were exactly what we thought they were, these perfect cosmic traps. Instead, he stumbled upon something that would shake the very foundations of physics. He discovered that black holes aren't perfectly black at all. They glow. They emit radiation. They slowly evaporate. This revelation didn't just challenge our understanding of black holes. It created a crisis in physics that we're still trying to resolve today. Because if black holes can emit radiation and eventually disappear, what happens to all the information that fell into them? Does it vanish from the universe forever, breaking one of the most fundamental laws of quantum mechanics? Or does it somehow escape, encoded in the radiation itself? The implications are staggering. If Hawking is right, then every black hole in the universe is engaged in an incredibly slow dance of self-destruction. The smallest ones might evaporate in less than a second, while the largest ones will outlive the death of every star in the universe, taking longer to disappear than most of us can even comprehend. We're talking about time frames that make the age of the universe look like a blink of an eye. But here's what makes this discovery even more remarkable. We've never actually seen Hawking radiation. Despite decades of searching with our most powerful telescopes and most sensitive instruments, this phenomenon remains theoretical. We're basing our understanding of the universe on mathematics so elegant and logic so compelling that we're willing to accept it even without direct observation. That's how confident physicists are in Hawking's work. This journey we're about to take together will challenge everything you think you know about the universe. We'll explore cosmic monsters that bend space and time, dive into the bizarre world of quantum mechanics where particles appear and disappear out of nothing, and witness how the collision of two very different theories of physics led to one of the most beautiful discoveries in science. We'll uncover why this discovery matters for every single atom in your body, why it tells us something fundamental about the nature of information itself, and why it might hold the key to understanding how the universe will end. Because Hawking radiation isn't just about black holes. It's about the ultimate fate of everything that exists. The story of Hawking radiation is really the story of human curiosity at its finest. It's about a scientist who refused to accept the obvious, who dared to ask what happens when the immovable object of general relativity meets the unstoppable force of quantum mechanics. What he found was a universe far more strange, far more beautiful, and far more mysterious than anyone had imagined. Prepare yourself for a journey that will take you from the event horizons of black holes to the very edge of human knowledge, where the line between the possible and impossible becomes beautifully blurred. The universe harbors entities so extraordinary that they fundamentally challenge our comprehension of reality itself. These cosmic phenomena possess gravitational fields of such overwhelming intensity that they render the very concept of escape meaningless. We are examining black holes, astronomical objects that represent the most extreme manifestation of gravity's dominion over space and time. To truly appreciate the revolutionary nature of Hawking radiation, we must first establish a comprehensive understanding of these enigmatic structures. Black holes are not merely cosmic curiosities, they are laboratories where the most fundamental laws of physics are tested under the most extreme conditions imaginable. Their existence forces us to confront the limits of human understanding and the boundaries of physical reality. The conceptual framework for black holes emerged from humanity's relentless pursuit of understanding gravity's ultimate expression. During the 18th century, two remarkable minds independently arrived at a startling conclusion that would prove prophetic. John Michel, a British natural philosopher, and Pierre-Simon Laplace, the distinguished French mathematician, both contemplated the theoretical possibility of celestial bodies possessing such immense gravitational attraction that even light itself could not achieve escape velocity. Their calculations, though primitive by contemporary standards, revealed a profound truth about the universe's architecture. They recognized that if matter could be compressed to sufficient density, it would create a gravitational field so intense that it would trap electromagnetic radiation within its influence. This insight represented humanity's first glimpse into the theoretical foundation of what we now recognize as black holes. However, these early visionaries lacked the mathematical framework necessary to fully explore their implications. Their work remained largely theoretical speculation until the early 20th century, when Albert Einstein's revolutionary theory of general relativity provided the conceptual tools required to understand these cosmic phenomena comprehensively. Einstein's field equations, formulated in 1915, described gravity not as a force but as a curvature of space-time itself. This paradigm shift transformed our understanding of gravitational phenomena from Newtonian mechanics to a geometric interpretation of the universe's structure. Within this new framework, massive objects literally bend the fabric of space-time, creating the gravitational effects we observe. The mathematical implications of Einstein's work were immediately recognized by Carl Schwarzschild, a German physicist and astronomer who tragically died shortly after during World War I. Schwarzschild solved Einstein's field equations for the specific case of a spherically symmetric, non-rotating massive object. His solution, known as the Schwarzschild metric, provided the first rigorous mathematical description of what we now understand as a black hole. Schwarzschild's work revealed that Einstein's equations predicted the existence of a critical radius, later termed the Schwarzschild radius, within which the curvature of spacetime becomes so extreme that escape becomes impossible. This mathematical breakthrough established the theoretical foundation for modern black hole physics, though decades would pass before observational evidence would confirm their existence. The transition from theoretical prediction to observational reality occurred gradually throughout the 20th century. The identification of Cygnus X-1 in 1971 as a black hole candidate marked a pivotal moment in astrophysics. This binary system, consisting of a blue supergiant star and an invisible companion of extraordinary mass, provided the first compelling evidence for black holes' existence in nature. A black hole represents a region of space-time where gravitational effects have become so pronounced that they create a boundary beyond which no information can escape to the external universe. This definition, though seemingly straightforward, encompasses profound implications for our understanding of physics, information theory, and the fundamental nature of reality itself. The formation of stellar black holes occurs through the catastrophic collapse of massive stars. When a star with initial mass exceeding approximately 25 solar masses exhausts its nuclear fuel, the outward pressure generated by fusion reactions can no longer counteract the inward pull of gravity. The resulting collapse occurs with such rapidity and intensity that the star's core becomes compressed to a point of theoretically infinite density, known as a singularity. During this collapse, the star's outer layers are expelled in a spectacular supernova explosion, while the core continues its relentless compression. The gravitational field surrounding the collapsed core becomes so intense that it warps space-time to an extreme degree, creating a region from which no signal, particle or form of energy can escape once it crosses a specific boundary. This boundary, termed the event horizon, represents the point of no return in the most literal sense. The event horizon is not a physical surface, but rather a mathematical construct that defines the region where the escape velocity equals the speed of light. Since nothing can travel faster than light, anything crossing this boundary becomes permanently trapped within the black hole's gravitational influence. The physics governing black holes challenges our conventional understanding of space and time. Within the event horizon, the normal relationship between space and time becomes distorted beyond recognition. The singularity at the center represents a point where the known laws of physics break down completely, creating what physicists term a naked singularity, if not hidden behind an event horizon. Black holes exhibit remarkable diversity in their properties, masses, and formation mechanisms. This diversity provides crucial insights into the universe's evolution and the various processes that govern stellar and galactic dynamics. Understanding these different classifications is essential for comprehending the full scope of black hole physics and their role in cosmic evolution. Stellar black holes formed through the gravitational collapse of massive stars represent the most common type of black hole in the universe. These objects typically possess masses ranging from approximately 3 solar masses to several hundred solar masses. The lower limit is determined by the Chandrasekhar limit and subsequent neutron degeneracy pressure, while the upper limit reflects the maximum mass that can be sustained by stellar nucleosynthesis processes. The formation process of stellar black holes is intrinsically linked to stellar evolution and the nuclear processes that govern a star's life cycle. Stars with initial masses exceeding the threshold for black hole formation undergo a complex sequence of nuclear burning phases, each characterized by the fusion of progressively heavier elements. When silicon burning is exhausted, no further nuclear process can provide sufficient outward pressure to counteract gravitational collapse. Supermassive black holes residing at the centers of galaxies represent another fundamental class of these cosmic entities. These objects possess masses ranging from millions to billions of solar masses, with some exceptional cases exceeding 10 billion solar masses. The formation mechanisms for supermassive black holes remain an active area of research, with several competing theories attempting to explain their existence and growth. The relationship between supermassive black holes and their host galaxies has emerged as one of the most significant discoveries in modern astrophysics. Observational evidence suggests a strong correlation between the mass of a galaxy's central black hole and properties of the galaxy's bulge, including stellar velocity dispersion and total mass. This correlation implies a deep connection between black hole growth and galactic evolution. Intermediate mass black holes occupy the mass range between stellar and supermassive black holes, typically containing hundreds to thousands of solar masses. These objects are considerably more elusive than their smaller and larger counterparts, with only a handful of confirmed detections. Their existence has important implications for understanding the formation and evolution of supermassive black holes. Primordial black holes represent a theoretical class of black holes that could have formed in the early universe through the direct collapse of density fluctuations rather than stellar evolution. These objects could potentially possess masses ranging from subatomic scales to stellar masses, depending on the specific conditions present during their formation epoch. The event horizon represents one of the most profound concepts in theoretical physics, marking the boundary between the observable universe and a region of space-time from which no information can escape. This boundary is not merely a mathematical abstraction, but has profound implications for our understanding of causality, information theory, and the fundamental nature of physical reality. The mathematical definition of the event horizon emerges naturally from the Schwarzschild solution to Einstein's field equations. For a non-rotating spherically symmetric black hole, the event horizon is located at the Schwarzschild radius, which equals twice the gravitational mass times the gravitational constant divided by the speed of light squared. This seemingly simple formula encapsulates profound physics about the relationship between mass, space, and time. The physical interpretation of the event horizon reveals its fundamental importance in black hole physics. At this boundary, the escape velocity equals the speed of light, making escape impossible for any material object or electromagnetic signal. This condition creates a one-way membrane in space-time, allowing matter and energy to enter but preventing any information about the interior from reaching external observers. The experience of crossing an event horizon presents a fascinating study in relativistic physics. For an observer falling into a black hole, the event horizon appears unremarkable during the crossing process. Local physics remains unchanged, and the falling observer experiences no unusual effects at the moment of crossing. However, due to gravitational time dilation, external observers would witness the falling observer's image becoming increasingly redshifted and time-dilated, appearing to freeze at the event horizon. This apparent paradox highlights the observer-dependent nature of event horizons and the importance of reference frames in relativistic physics. The event horizon's location depends on the observer's position and motion, emphasizing that black holes are not simply objects, but rather regions of space-time with specific causal structure. The thermodynamic properties of event horizons have emerged as a crucial area of research, particularly following the work of Jacob Bekenstein and Stephen Hawking. The recognition that event horizons possess entropy proportional to their surface area has led to profound insights into the relationship between gravity, thermodynamics, and information theory. This connection forms the foundation for understanding Hawking radiation and the information paradox that continues to challenge our comprehension of black hole physics. The study of event horizons also reveals important connections to other areas of theoretical physics, including quantum field theory and string theory. The behavior of quantum fields near event horizons has provided crucial insights into the nature of vacuum fluctuations and the relationship between quantum mechanics and general relativity. Understanding event horizons is essential for appreciating the revolutionary nature of Hawking's discovery. These boundaries, once thought to be absolute barriers preventing any escape from black holes, become the stage where quantum mechanics and general relativity interact to produce the subtle but profound phenomenon of Hawking radiation. The event horizon thus represents not merely a boundary, but a laboratory where the most fundamental aspects of physics are tested and revealed. Beyond the event horizon lies a realm where our most fundamental understanding of physics encounters its ultimate test. This chapter serves as our gateway into the mysterious interior of black holes, where we must confront the extraordinary physics that governs these cosmic entities and examine the classical assumptions that Stephen Hawking would eventually challenge. The interior of a black hole represents one of the most extreme environments conceivable in our universe. Here, the familiar laws of physics are stretched to their absolute limits, creating conditions so extraordinary that they force us to question the very nature of space, time, and reality itself. Understanding these extreme conditions becomes essential for appreciating the revolutionary nature of Hawking's later discovery. At the very center of every black hole lies what physicists term the singularity, a mathematical point where the curvature of space-time becomes infinite and our conventional understanding of physics breaks down completely. This singularity represents far more than simply a very dense object. It constitutes a fundamental boundary in our comprehension of the universe itself. The singularity presents us with a profound conceptual challenge. According to general relativity, all the matter that falls into a black hole becomes compressed into this single point of infinite density. The mathematical equations that describe this state contain infinities, which typically signal that our theoretical framework has reached its limits. When physicists encounter infinities in their calculations, this usually indicates that new physics must emerge to provide a more complete description of the phenomenon. Consider the extraordinary nature of this compression. Every atom, every subatomic particle, every quantum of energy that crosses the event horizon eventually reaches this central point. The normal structure of matter, held together by electromagnetic forces and quantum mechanical principles, cannot withstand the extreme gravitational forces present near the singularity. The very concepts of distance and duration, which form the foundation of our understanding of space and time, become meaningless in this environment. The singularity challenges our deepest assumptions about the nature of reality. In our everyday experience, we understand that information about objects persists even when the objects themselves are destroyed. When a book burns, the information it contained may be lost to us, but the fundamental particles that composed it continue to exist in some form. The singularity, however, appears to represent a point where this principle breaks down entirely. This breakdown of conventional physics at the singularity creates what physicists call a naked singularity problem. If singularities could exist without being hidden behind event horizons, they would represent regions where the laws of physics simply do not apply, creating unpredictable effects that could influence the rest of the universe. The cosmic censorship hypothesis, proposed by Roger Penrose, suggests that nature somehow prevents naked singularities from forming, always shrouding them behind event horizons. The classical view of black holes, derived from Einstein's general relativity, presents them as perfect cosmic prisons from which nothing can escape. This perspective dominated our understanding for decades and created what seemed to be an insurmountable theoretical barrier. Understanding this classical view becomes crucial for appreciating the revolutionary nature of Hawking's later insights. Einstein's field equations demonstrate that massive objects curve the fabric of space-time, creating what we perceive as gravitational attraction. In the case of black holes, this curvature becomes so extreme that it creates a region from which light itself cannot escape. The event horizon marks the boundary of this region, representing the point of no return for any object or signal. The mathematics of general relativity reveals that the event horizon acts as a one-way membrane. Information and matter can cross from the outside universe into the black hole, but the reverse journey becomes impossible according to classical physics. This creates a fundamental asymmetry in the flow of information and energy in the universe. Once something crosses the event horizon, it becomes causally disconnected from the external universe, unable to send any signal or exert any influence on the outside world. This classical picture creates several profound implications for our understanding of the universe. First, it suggests that black holes can only grow, never shrink. Every particle of matter, every photon of light that falls into a black hole adds to its mass and increases the size of its event horizon. This leads to the conclusion that black holes are eternal objects that will persist indefinitely, accumulating matter and energy throughout the lifetime of the universe. The classical view also implies that black holes are perfectly efficient destroyers of information. Any complex structure, any organized system, any meaningful pattern that falls into a black hole becomes permanently lost to the universe. This appears to violate a fundamental principle of physics known as unitarity, which states that information cannot be truly destroyed, only transformed. Furthermore, the classical description suggests that black holes are perfectly black, emitting no radiation whatsoever. They absorb everything and release nothing, making them invisible except for their gravitational effects on nearby matter. This perfect blackness seemed to be a fundamental feature of these objects, derived directly from the most successful theory of gravity we possess. The classical conundrum becomes even more puzzling when we consider the thermodynamic properties of black holes. Jacob Bekenstein's work in the early 1970s suggested that black holes should possess entropy, a measure of disorder or information content. However, if black holes are perfectly black and can only absorb matter and energy, how can they maintain thermal equilibrium with their surroundings? How can they possess temperature without emitting radiation? This classical framework created a theoretical tension that demanded resolution. The equations of general relativity appeared to be complete and self-consistent, yet they led to conclusions that seemed to violate other fundamental principles of physics. The stage was set for a theoretical breakthrough that would require looking beyond classical physics to the quantum realm. The resolution to this classical conundrum would ultimately come from recognizing that our understanding of black holes was incomplete. While general relativity provides an excellent description of strong gravitational fields, it does not account for the quantum mechanical nature of matter and energy. Near the event horizon of a black hole, where gravitational fields are extremely strong, but the curvature of spacetime varies rapidly over quantum-scale distances, the effects of quantum mechanics become crucial for understanding the complete physics of these systems. This quantum perspective would reveal that the classical view of black holes as perfect prisms is an approximation that breaks down when we consider the full quantum nature of reality. The prison walls of the event horizon, while impermeable to classical physics, become permeable to quantum effects, allowing for processes that were previously thought to be impossible. The universe operates according to two fundamental sets of rules, and for most of human history, we believed these rules governed completely separate domains. On one side, we have Einstein's general relativity, which describes how massive objects bend the fabric of space-time itself. On the other side, we have quantum mechanics, which reveals the bizarre behavior of particles at the smallest scales imaginable. These two theories represent the greatest intellectual achievements in physics, yet they seem to describe entirely different universes. General relativity tells us that massive objects create curvatures in space-time, and these curvatures are what we experience as gravity. When we observe a planet orbiting a star, we are witnessing the planet following the straightest possible path through curved space-time. This theory has been validated countless times, from the precise orbit of Mercury to the detection of gravitational waves from colliding black holes. It describes our universe as smooth, continuous, and deterministic. Quantum mechanics, however, presents us with a fundamentally different reality. At the quantum level, particles exist in states of probability rather than definite locations. An electron does not orbit an atom's nucleus like a planet around a star. Instead, it exists in a cloud of probability, simultaneously occupying all possible positions until the moment we observe it. This theory has given us lasers, computers, and our understanding of how atoms bond to form molecules. It describes our universe as inherently uncertain, probabilistic, and fundamentally discrete. The mathematical frameworks of these theories are not merely different, they are seemingly incompatible. General relativity treats space-time as a continuous fabric that can be curved and stretched. Quantum mechanics treats energy and matter as coming in discrete packages called quanta, and it introduces fundamental limits to how precisely we can know certain properties of particles simultaneously. The famous Heisenberg uncertainty principle tells us that we cannot simultaneously know both the exact position and momentum of a particle with perfect precision. For decades, physicists have been content to use general relativity for describing large-scale phenomena like stars, galaxies, and the expansion of the universe, while applying quantum mechanics to atomic and subatomic processes. This division of labor has been remarkably successful, enabling us to understand everything from the nuclear reactions that power stars to the electronic devices that define modern civilization. However, there exist certain extreme environments in our universe where these two theories must inevitably collide. Black holes represent perhaps the most dramatic example of such an environment. The immense gravitational fields near a black hole's event horizon create conditions where the smooth space-time of general relativity meets the quantum vacuum of quantum field theory. In these regions, we can no longer treat space-time as a simple, continuous background upon which quantum processes occur. The event horizon of a black hole presents us with a unique laboratory for studying this collision between theories. According to general relativity, the event horizon is simply a boundary in space-time, not a physical surface. An observer falling through the event horizon would not experience anything unusual at the moment of crossing. From their perspective, space-time remains smooth and continuous. However, quantum mechanics tells us that even empty space is not truly empty. This brings us to one of the most profound and counterintuitive concepts in modern physics. The quantum vacuum represents one of the most remarkable discoveries of 20th century physics. What we commonly think of as empty space is actually a seething sea of activity at the quantum level. The Heisenberg uncertainty principle, which we typically associate with the inability to simultaneously measure a particle's position and momentum, has a temporal counterpart. This uncertainty relation tells us that energy and time are related in a fundamental way that allows for extraordinary phenomena. Over extremely short time intervals, the uncertainty principle permits violations of energy conservation. These violations manifest as the spontaneous creation of particle-antiparticle pairs from the quantum vacuum itself. A photon of light can briefly split into an electron and a positron, its antimatter counterpart. A region of space that appears completely empty can suddenly produce a pair of quarks and antiquarks. These particles, called virtual particles, exist for only the briefest instant before they must annihilate each other and return their borrowed energy to the vacuum. The term virtual might suggest that these particles are somehow less real than ordinary particles, but this interpretation would be profoundly misleading. Virtual particles produce measurable effects in our universe. They are responsible for the Casimir effect, where two parallel metal plates in a vacuum experience a tiny attractive force due to the altered quantum vacuum between them. They contribute to the magnetic moment of the electron, which has been measured to an accuracy of better than 1 part in a trillion. Virtual particles are as real as any other quantum phenomenon, distinguished only by their extremely brief existence. The quantum vacuum is therefore not empty in any meaningful sense. It is a dynamic, fluctuating medium where particle-antiparticle pairs are constantly being created and destroyed. The rate of these fluctuations depends on the energy scale we are examining. At higher energies, corresponding to shorter timescales, the fluctuations become more violent and more frequent. The vacuum near a black hole's event horizon represents one of the most extreme environments in the universe, where the effects of these quantum fluctuations become amplified by the intense gravitational field. When we consider the region immediately outside a black hole's event horizon, we encounter a situation where the smooth space-time of general relativity meets the fluctuating quantum vacuum of quantum field theory. The intense gravitational field near the event horizon affects the behavior of virtual particle pairs in ways that classical physics cannot predict. The curvature of space-time itself becomes so extreme that it can influence the creation and annihilation of virtual particles. This is where the true genius of Stephen Hawking's insight becomes apparent. Hawking realized that the presence of the event horizon fundamentally alters the behavior of virtual particle pairs. In flat space-time far from any massive objects, virtual particles appear and disappear in perfect symmetry. Every particle has its antiparticle partner, and they inevitably find each other and annihilate, returning their borrowed energy to the vacuum. However, near the event horizon of a black hole, this symmetry can be broken. The intense gravitational field and the presence of the event horizon itself create conditions where the normal process of particle-antiparticle annihilation can be disrupted. A virtual particle pair created just outside the event horizon might find itself in a situation where one member of the pair falls across the event horizon while the other escapes to infinity. This separation of virtual particle pairs has profound consequences for our understanding of black holes. The particle that escapes to infinity cannot return to annihilate with its partner, which is now trapped behind the event horizon. This escaped particle becomes real, carrying away energy from the black hole system. The particle that falls into the black hole carries negative energy, actually reducing the black hole's total mass energy. The mathematical description of this process requires sophisticated techniques from quantum field theory in curved space-time. The calculations involve determining how the quantum vacuum state near the event horizon differs from the vacuum state far from the black hole. This difference in vacuum states is what allows for the net production of real particles at the expense of the black hole's mass. The energy for this process comes from the black hole itself, specifically from its gravitational field. As virtual particles are converted into real particles through this mechanism, the black hole loses mass according to Einstein's famous equation E equals mc squared. The escaping radiation carries away energy, causing the black hole to shrink gradually over time. This process represents a fundamental connection between the quantum properties of the vacuum and the classical geometry of space-time. The implications of this quantum process extend far beyond black hole physics. It suggests that the universe at its most fundamental level is governed by an intricate interplay between quantum mechanics and general relativity. The smooth, deterministic space-time of Einstein's theory becomes populated with quantum fluctuations that can have macroscopic consequences. The discrete, probabilistic world of quantum mechanics extends its influence to the largest scales in the universe. This quantum mechanical process near black holes also reveals something profound about the nature of information in physics. The virtual particles that become real carry away not just energy, but potentially information about the black hole itself. This raises fundamental questions about whether information that falls into a black hole can ever truly be lost, or whether it somehow becomes encoded in the radiation that escapes. The collision between quantum mechanics and general relativity near black holes has opened up entirely new fields of research in theoretical physics. Scientists now study quantum gravity, string theory, and loop quantum gravity in attempts to develop a complete theory that can describe both quantum phenomena and gravitational effects in a unified framework. The insights gained from understanding Hawking radiation have influenced our thinking about the early universe, the nature of space-time itself, and the ultimate fate of our cosmos. The quantum whispers from the void near black holes have revealed that our universe is far stranger and more interconnected than we ever imagined. The boundary between the quantum and classical worlds is not as sharp as we once believed, and the most extreme environments in our universe serve as laboratories for exploring the deepest mysteries of physical reality. The year 1974 marked a turning point in theoretical physics that would fundamentally alter our comprehension of the universe. What emerged from Stephen Hawking's calculations was not merely another scientific theory, but a revolutionary paradigm that challenged the very foundations of black hole physics. To understand the magnitude of this breakthrough, we must first examine the intellectual groundwork laid by pioneering researchers who dared to question the absolute nature of black holes. The seeds of what would become Hawking radiation were planted in the fertile minds of Soviet physicists Yakov Zeldovich and Alexei Starobinsky during the early 1970s. These brilliant scientists possessed the audacity to challenge the prevailing orthodoxy that black holes were perfectly inert cosmic entities. Their revolutionary propositions suggested that rotating black holes, known as Kerr black holes, could potentially emit particles through quantum mechanical processes. Zeldovich and Starobinsky's work focused on a specific phenomenon called superradiance, where electromagnetic waves or particles could extract energy from a rotating black hole's ergosphere. The ergosphere represents the region outside the event horizon where space-time itself is dragged around by the black hole's rotation. Within this twisted realm of space-time, they discovered that certain quantum fluctuations could be amplified rather than absorbed, leading to the emission of real particles. Their mathematical investigations revealed that when quantum fields interacted with the curved space-time geometry near rotating black holes, something extraordinary occurred. The rotational energy of the black hole could be transferred to quantum fluctuations, transforming virtual particles into real ones that could escape to infinity. This process suggested that black holes were not the perfect absorbers that classical physics had predicted, but could actually give back energy to the universe under specific circumstances. However, their groundbreaking work contained a crucial limitation. The particle emission they described was restricted to rotating black holes and required very specific conditions. Non-rotating black holes, known as Schwarzschild black holes, remained seemingly immune to this quantum leakage. This restriction would prove to be a significant constraint, as it meant that the vast majority of black holes in the universe would still be considered perfectly black according to their calculations. The implications of Zeldovich and Starobinsky's discoveries were profound, yet the scientific community remained largely skeptical. The idea that black holes could emit anything contradicted decades of established understanding. Nevertheless, their work established a critical precedent by demonstrating that quantum mechanics could indeed influence black hole behavior in unexpected ways. This intellectual foundation would prove essential for the even more revolutionary discovery that was about to emerge. Jacob Bekenstein entered the stage of black hole physics with a proposition so audacious that it initially provoked fierce resistance from the scientific establishment, including Stephen Hawking himself. Bekenstein's revolutionary insight centered on the concept of entropy, a fundamental quantity in thermodynamics that measures the degree of disorder or the number of microscopic configurations that correspond to a macroscopic state. The traditional understanding of entropy was firmly rooted in systems containing ordinary matter and energy. However, Bekenstein proposed that black holes themselves possessed entropy, and furthermore, that this entropy was proportional to the area of the black hole's event horizon rather than its volume. This proposition was revolutionary because it suggested that black holes were not merely gravitational anomalies, but were thermodynamic entities with well-defined statistical properties. Bekenstein's reasoning was elegant in its simplicity, yet profound in its implications. He argued that when matter falls into a black hole, it carries with it information about its quantum state. This information could not simply disappear from the universe without violating fundamental principles of quantum mechanics. Therefore, the information must be encoded somehow in the black hole's structure, contributing to its entropy. The mathematical relationship Bekenstein proposed was startling in its precision. He suggested that the entropy of a black hole was equal to 1/4 of its event horizon area, measured in Planck units. This relationship, known as the Bekenstein bound, established a fundamental connection between gravity, quantum mechanics, and information theory. It implied that black holes were not featureless objects, but possessed an enormous number of internal microstates that could account for their entropy. The scientific community's initial reaction to Bekenstein's proposal was overwhelmingly negative. The idea that black holes possessed temperature and entropy seemed to violate the basic understanding of thermodynamics. After all, how could an object have temperature without emitting thermal radiation? The laws of thermodynamics seem to demand that any system with non-zero entropy must be capable of heat exchange with its surroundings. Stephen Hawking himself was among the most vocal critics of Bekenstein's theory. Hawking argued that if black holes possessed entropy, they would necessarily have to emit radiation to maintain thermal equilibrium with their surroundings. Since black holes were universally understood to be perfect absorbers, incapable of emission, Hawking considered Bekenstein's proposal to be fundamentally flawed. However, Bekenstein's work contained a crucial insight that would prove prophetic. He recognized that the marriage of quantum mechanics with general relativity in the extreme gravitational environment near black holes could produce unexpected phenomena. His bold claim that black holes possessed entropy would soon be vindicated in the most spectacular fashion imaginable. Stephen Hawking's journey toward his revolutionary discovery began with a mission to definitively disprove Bekenstein's controversial entropy theory. Armed with the mathematical tools of quantum field theory and general relativity, Hawking set out to demonstrate once and for all that black holes could not emit radiation. The irony of scientific discovery would soon reveal itself as Hawking's attempt to refute Bekenstein led to one of the most profound insights in the history of physics. Hawking's approach involved applying the principles of quantum field theory to the curved space-time geometry surrounding black holes. Quantum field theory describes the behavior of particles and fields at the smallest scales, where the uncertainty principle of quantum mechanics becomes paramount. In flat space-time, this theory predicts that even empty space is filled with quantum fluctuations, virtual particle pairs that spontaneously appear and annihilate each other over extremely short time intervals. The critical insight came when Hawking considered what happens to these quantum fluctuations in the presence of a black hole's intense gravitational field. Near the event horizon, the curvature of space-time becomes so extreme that it can affect the delicate balance of virtual particle creation and annihilation. The gravitational field essentially acts as a catalyst, transforming some of these virtual particles into real particles that can escape to infinity. The mechanism underlying this process is both elegant and subtle. When a virtual particle pair is created near the event horizon, the intense gravitational field can separate the pair before they have a chance to annihilate each other. One particle falls into the black hole while its partner escapes, carrying away a small amount of energy. From the perspective of distant observers, the black hole appears to be emitting a steady stream of particles, creating what we now call Hawking radiation. The mathematical calculations revealed that this radiation has a perfectly thermal spectrum, characterized by a temperature that is inversely proportional to the black hole's mass. This relationship, known as the Hawking temperature, means that more massive black holes are paradoxically colder than smaller ones. A black hole with the mass of our Sun would have a temperature of approximately 60 nanokelvins, which is incredibly cold compared to the cosmic microwave background radiation at 2.7 Kelvin. The energy for this radiation comes from the black hole's own mass, following Einstein's famous equation E=mc². As the black hole emits radiation, it gradually loses mass, causing it to shrink and become hotter. This creates a positive feedback loop where the emission rate increases as the black hole becomes smaller, ultimately leading to complete evaporation in a final burst of energy. Hawking's calculations demonstrated that Bekenstein's entropy formula was not only correct, but was a natural consequence of the quantum mechanical emission process. The temperature of the radiation was precisely what thermodynamics predicted for a system with Bekenstein's proposed entropy. This remarkable convergence of independent theoretical approaches provided compelling evidence for the reality of black hole evaporation. The scientific community's response to Hawking's revolutionary theory was characterized by a complex mixture of fascination, skepticism, and gradual acceptance. The announcement of Hawking radiation challenged fundamental assumptions about the nature of black holes and forced physicists to reconsider their understanding of the relationship between quantum mechanics and gravity. Initial skepticism was both widespread and understandable. The idea that black holes could emit radiation contradicted decades of established physics. Many physicists questioned whether Hawking's mathematical techniques were applicable to the extreme conditions near black holes. The concept of applying quantum field theory in curved spacetime was still relatively new, and the validity of the approximations used in the calculations was subject to debate. One of the primary concerns raised by critics was the apparent violation of energy conservation. If black holes could emit radiation, where did the energy come from? Hawking's explanation that the energy came from the black hole's own mass, causing it to shrink, seemed counterintuitive. The notion that smaller black holes would be hotter than larger ones ran counter to everyday experience and required a fundamental shift in thinking about thermodynamic systems. The theoretical framework underlying Hawking's discovery also faced scrutiny. The calculation involved sophisticated mathematical techniques from quantum field theory, general relativity, and statistical mechanics. Verifying these calculations required expertise in multiple areas of theoretical physics, and many researchers initially approached the results with caution until they could independently verify the mathematical derivations. However, as more physicists worked through Hawking's calculations, the mathematical rigor and internal consistency of the theory became increasingly apparent. The discovery that black holes possessed all the thermodynamic properties predicted by Bekenstein's entropy formula provided powerful corroborating evidence. The temperature derived from the radiation spectrum matched exactly with the temperature predicted by thermodynamic considerations, creating a beautiful theoretical unity. The acceptance of Hawking radiation was further accelerated by the confirmation of related predictions. The area theorem, which Hawking had proven earlier, demonstrated that the total area of event horizons could never decrease in any physical process. This theorem was perfectly consistent with the thermodynamic interpretation of black holes, where the area played the role of entropy. The scientific community's embrace of Hawking radiation was also influenced by its profound implications for fundamental physics. The theory provided the first concrete example of a phenomenon that required both quantum mechanics and general relativity for its explanation. This suggested that Hawking radiation might offer crucial insights into the long-sought theory of quantum gravity. Perhaps most importantly, Hawking radiation resolved the apparent contradiction between black hole physics and the laws of thermodynamics. By demonstrating that black holes could emit radiation and possessed well-defined thermodynamic properties, Hawking's theory restored consistency to our understanding of the physical world. The universe once again made sense, albeit in a far more subtle and beautiful way than anyone had previously imagined. The gradual acceptance of Hawking radiation marked a watershed moment in theoretical physics. It demonstrated that even the most fundamental assumptions about the nature of reality could be overturned by careful mathematical analysis and deep physical insight. The theory established Stephen Hawking as one of the leading theoretical physicists of his generation, and opened up entirely new avenues of research that continue to influence our understanding of the universe today. The revelation that black holes emit radiation fundamentally transforms our understanding of these cosmic entities from eternal prisons into temporary phenomena. This discovery compels us to examine the precise mechanisms underlying this extraordinary process and confront the profound implications for the ultimate destiny of every black hole in the universe. The mathematics governing Hawking radiation reveal a universe operating on principles far more intricate than classical physics suggested. When we delve into the quantum mechanical processes occurring near the event horizon, we encounter phenomena that challenge our most basic assumptions about the permanence of massive objects and the conservation of energy on cosmic scales. The mechanism through which black holes lose mass represents one of the most elegant demonstrations of quantum mechanics operating on macroscopic scales. Near the event horizon of any black hole, the intense gravitational field creates conditions where quantum field theory produces extraordinary effects that classical physics cannot explain. The quantum vacuum, rather than being empty space, seethes with virtual particle pairs that spontaneously appear and annihilate within incredibly brief time frames. These virtual particles, consisting of matter and antimatter counterparts, normally exist for periods so short that they cannot be directly observed. However, the extreme curvature of space-time near a black hole's event horizon disrupts this delicate balance in a remarkable way. When virtual particle pairs emerge near the event horizon, the intense gravitational gradient can separate them before they annihilate. This separation occurs because the gravitational field varies dramatically over the tiny distance separating the particle pair. The particle closer to the black hole experiences significantly stronger gravitational attraction than its partner, potentially causing them to be torn apart before mutual annihilation can occur. In this extraordinary process, one particle from the pair falls irreversibly across the event horizon while its partner escapes to infinity. The escaping particle becomes real radiation that we can, in principle, observe. This transformation from virtual to real particles requires energy, which must be supplied by the black hole itself. Consequently, the black hole loses mass equal to the energy of the escaping particle, gradually diminishing over time. The energy required to create these real particles comes from the black hole's gravitational binding energy. As the black hole provides this energy, its mass decreases infinitesimally with each particle that escapes. This process, though occurring at an incredibly slow rate for stellar mass black holes, represents genuine mass loss that accumulates over vast timescales. The mathematical description of this process reveals that the rate of mass loss depends critically on the black hole's surface gravity at the event horizon. Smaller black holes with higher surface gravity emit radiation more rapidly than their more massive counterparts. This relationship establishes a fundamental connection between the black hole's mass and its evaporation rate. The concept of black hole temperature emerges naturally from the analysis of Hawking radiation and provides profound insights into the thermal properties of these exotic objects. The temperature of a black hole, known as the Hawking temperature, exhibits a remarkable inverse relationship with the black hole's mass that defies our everyday understanding of thermal physics. The Hawking temperature formula reveals that black holes become hotter as they become smaller. This counterintuitive relationship means that the most massive black holes in the universe possess the lowest temperatures, while hypothetical microscopic black holes would be extraordinarily hot. For a black hole with the mass of our Sun, the Hawking temperature measures approximately 60 nanokelvins, which is incredibly cold compared to the cosmic microwave background radiation at 2.7 Kelvin. This inverse temperature-mass relationship has profound implications for black hole evolution. As a black hole emits radiation and loses mass, it becomes progressively hotter, causing it to radiate even more intensely. This creates a runaway process where the evaporation rate accelerates as the black hole shrinks. The smaller the black hole becomes, the faster it evaporates, leading to what physicists term a thermal runaway effect. The temperature of a black hole also determines the spectrum of radiation it emits. Just as hot objects emit light at different wavelengths depending on their temperature, black holes emit particles and radiation across a spectrum determined by their Hawking temperature. Larger black holes emit primarily low-energy photons and particles, while smaller black holes can emit high-energy gamma rays and even massive particles. For supermassive black holes containing millions or billions of solar masses, the Hawking temperature becomes so low that the radiation consists almost entirely of extremely low-energy photons. These photons carry so little energy that the black hole's evaporation rate becomes negligible compared to other processes affecting its mass, such as accretion of surrounding matter. The temperature also affects which types of particles the black hole can emit. Massive particles require more energy to create than massless ones, so only the hottest black holes can emit particles like electrons, protons, or heavier species. This creates a natural hierarchy where the evaporation products depend critically on the black hole's mass and corresponding temperature. The ultimate destiny of black holes through Hawking radiation depends entirely on their initial mass and the environment in which they exist. This dependence creates a fascinating spectrum of evolutionary pathways that reveal the diverse fates awaiting different classes of black holes throughout cosmic history. For stellar mass black holes, those formed from collapsed stars with masses between 3 and 100 times our Sun's mass, the evaporation process occurs over unimaginably long timescales. A black hole with the mass of our Sun would require approximately 10 to the power of 67 years to evaporate completely through Hawking radiation. To put this time frame in perspective, this duration exceeds the current age of the universe by a factor of 10 to the power of 57. Even the protons in ordinary matter are expected to decay long before such black holes complete their evaporation. Supermassive black holes, those giants residing at the centers of galaxies with masses ranging from millions to billions of solar masses, face even more extended evaporation timescales. These cosmic behemoths would require periods approaching 10 to the power of 100 years to evaporate completely. Such timescales transcend conventional understanding of permanence, extending far beyond the era when stars continue to shine and galaxies maintain their current structures. The evaporation process itself becomes increasingly dramatic as black holes approach the end of their existence. During the final stages of evaporation, when the black hole's mass has diminished to microscopic levels, the Hawking temperature becomes extraordinarily high. This extreme temperature enables the black hole to emit not only photons but also massive particles including electrons, positrons and even heavier species. The final moments of a black hole's existence involve a spectacular burst of energy release. As the black hole's mass approaches zero, its temperature approaches infinity, theoretically allowing it to emit particles of any mass. However, the detailed physics of this final explosion remains uncertain because our current theories break down when quantum gravitational effects become dominant. Some theoretical models suggest that black holes might not evaporate completely, but instead leave behind stable remnants with masses near the Planck scale. These hypothetical objects, sometimes called Planck mass relics, would represent the ultimate endpoint of black hole evaporation, containing all the information that originally fell into the black hole, compressed into a quantum gravitational object. The evaporation of primordial black holes, those theoretical objects formed in the early universe with masses potentially much smaller than stellar masses, presents entirely different scenarios. If primordial black holes with masses comparable to mountains existed, they would be evaporating now, potentially producing detectable gamma-ray signatures. Black holes with masses comparable to asteroids would have already evaporated, while those with masses comparable to the Earth would evaporate over timescales comparable to the age of the universe. The study of black hole evaporation also reveals profound connections to fundamental questions about the nature of space-time itself. As black holes evaporate, they potentially carry information about the quantum structure of space-time and the unification of quantum mechanics with general relativity. The final stages of evaporation might provide observational windows into physics beyond the standard model, revealing new particles or interactions that become accessible only at the extreme energies associated with quantum gravity. The fate of black holes through Hawking radiation thus represents far more than the simple disappearance of massive objects. It embodies our deepest questions about the nature of information, the structure of space-time, and the ultimate destiny of the universe itself. Each evaporating black hole potentially holds keys to understanding the most fundamental aspects of physical reality, making their study essential for comprehending the cosmos at its most basic level. The discovery of Hawking radiation introduced one of the most profound paradoxes in modern physics, a contradiction so fundamental that it threatens the very consistency of our understanding of reality. This is not merely an academic curiosity. This is a crisis that strikes at the heart of two of our most successful theories about the universe, forcing us to confront the possibility that our deepest assumptions about the nature of existence may be fundamentally flawed. To comprehend the magnitude of this paradox, we must first understand what physicists mean when they speak of information. In the classical world, information seems straightforward. The position of a baseball, the temperature of a cup of coffee, the arrangement of words on a page, all of these constitute information. However, in the quantum realm, information takes on a far more profound significance. In quantum mechanics, information encompasses the complete quantum state of every particle, every field, every interaction in the universe. This includes not merely the position and momentum of particles, but their quantum superpositions, their entanglement relationships, and their probability amplitudes. When physicists speak of preserving information, they are referring to the preservation of this complete quantum description of reality. The principle of information conservation is not merely a convenient assumption. It represents one of the most fundamental tenets of quantum mechanics, embedded in the mathematical structure of the theory itself. The evolution of quantum systems is governed by what we call unitary operators, mathematical transformations that preserve the total amount of information in the system. This means that if you know the complete quantum state of a system at one time, you can, in principle, calculate its state at any other time, forward or backward. Consider the profound implications of this principle. It suggests that the universe operates like a vast quantum computer, where information is never truly lost, only transformed. Every interaction, every collision, every decay process preserves the fundamental information content of the universe. This principle has been tested countless times in laboratory experiments, from the behavior of individual photons to the complex dynamics of many-body quantum systems. The paradox emerges when we apply this principle to black holes. According to Hawking's original calculations, the radiation emitted by an evaporating black hole is purely thermal, random and featureless, like the glow from a heated piece of metal. This thermal radiation carries no information about the specific matter that originally fell into the black hole. Whether the black hole formed from hydrogen atoms, iron nuclei, or the complete works of Shakespeare, the outgoing radiation would be identical. This presents us with a devastating contradiction. If a black hole can completely evaporate through Hawking radiation, leaving behind only thermal radiation, then all the information that fell into the black hole appears to have vanished from the universe forever. The detailed quantum states of every particle, every photon, every atom that crossed the event horizon would be irretrievably lost, violating the fundamental principle of information conservation. The implications extend far beyond black holes themselves. If information can be destroyed in nature, then the entire framework of quantum mechanics becomes internally inconsistent. The mathematical structure that governs atomic behavior, chemical reactions, and the operation of quantum computers would be fundamentally flawed. We would need to abandon one of the most successful theories in the history of science. Hawking himself initially embraced this conclusion, arguing that black holes represent the first known example of genuine information loss in physics. He proposed that we must abandon our attachment to information conservation and accept that certain physical processes can indeed destroy information. This was not a casual suggestion, but a profound challenge to the foundations of physics. The paradox becomes even more acute when we consider the perspective of different observers. From the viewpoint of someone falling into a black hole, nothing unusual happens as they cross the event horizon. They continue to carry their quantum information with them. However, from the perspective of an outside observer, this same information appears to be encoded in the Hawking radiation emitted by the black hole. This suggests that the same information exists in two places simultaneously, inside the black hole and in the outgoing radiation, a clear violation of the no-cloning theorem of quantum mechanics. The resolution of this paradox has occupied some of the brightest minds in theoretical physics for decades, leading to revolutionary insights that extend far beyond black hole physics. The breakthrough came from recognizing that the information paradox is intimately connected to the nature of quantum entanglement and the holographic principle. The first major advance came from the realization that the Hawking radiation cannot be truly thermal if information is to be preserved. Instead, the radiation must be subtly correlated with the quantum state of the matter that originally fell into the black hole. These correlations would be incredibly weak and would only become apparent after the black hole had evaporated more than half of its original mass, a point known as the Page time, named after physicist Don Page. This insight led to the derivation of the Page curve, a mathematical description of how information emerges from an evaporating black hole. Initially, as the black hole emits radiation, the entropy of the outside universe increases as expected for thermal radiation. However, at the Page time, this trend reverses. The entropy of the radiation begins to decrease, indicating that the later radiation carries specific information about the black hole's contents. The mechanism behind this information recovery involves quantum entanglement in ways that were previously unimaginable. Recent work has shown that the outgoing Hawking radiation becomes entangled with the quantum degrees of freedom inside the black hole in such a way that the information gradually leaks out. This process is described by the concept of entanglement islands, regions of space where quantum correlations extend across the event horizon. The entanglement island proposal suggests that the information inside a black hole is not truly isolated from the outside world. Instead, quantum correlations connect the interior of the black hole to the emitted radiation in ways that allow information to escape while preserving the principles of quantum mechanics. This represents a radical departure from our classical intuitions about locality and causality. These developments have been supported by advances in quantum gravity research, particularly in the context of the AD-CFT correspondence, a powerful theoretical framework that relates theories of gravity to quantum field theories. Using this correspondence, physicists have been able to calculate the Page curve explicitly and demonstrate that information is indeed preserved in the evaporation process. However, the resolution of the information paradox raises new questions that are equally profound. If information can escape from black holes, what does this tell us about the nature of space-time itself? The proposed mechanisms suggest that space-time may be fundamentally non-local at the quantum level, with correlations extending across regions that appear to be causally disconnected. The debate continues to evolve as new theoretical tools and computational techniques become available. Some physicists argue that the resolution requires us to abandon our classical notions of space-time altogether, embracing a more fundamental description of reality in terms of quantum information. Others propose that the event horizon itself may be more complex than previously thought, with subtle structures that allow information to escape through mechanisms we are only beginning to understand. The quest for a complete understanding of the information paradox remains one of the most active areas of research in theoretical physics. Each proposed solution opens new avenues of investigation and reveals deeper connections between quantum mechanics, gravity, and the nature of information itself. The paradox that began with Hawking's discovery of black hole radiation has evolved into a comprehensive exploration of the fundamental principles that govern our universe. The theoretical elegance of Hawking radiation presents us with one of the most profound challenges in experimental physics. Despite nearly 5 decades of rigorous mathematical validation, this phenomenon remains tantalizingly beyond our observational capabilities. The fundamental question that haunts the scientific community is whether we possess the technological sophistication to detect radiation so extraordinarily faint that it appears virtually indistinguishable from the cosmic background noise that permeates our universe. The mathematical predictions are unambiguous. Hawking radiation should exist wherever black holes exist. Yet the intensity of this radiation decreases dramatically with the mass of the black hole, creating what physicists describe as an inverse relationship of staggering proportions. For a black hole with the mass of our Sun, the temperature of the Hawking radiation would be approximately 60 nanokelvins, which is 600 billion times colder than the cosmic microwave background radiation that fills space. This temperature differential makes detection not merely challenging but seemingly impossible with current technological capabilities. However, the scientific community has not accepted defeat. Instead, researchers have developed 3 distinct approaches to validate Hawking's predictions, each representing a different philosophical approach to experimental verification. These methodologies encompass the search for naturally occurring sources of detectable Hawking radiation, the creation of laboratory analogues that simulate black hole conditions, and the development of increasingly sophisticated detection technologies that might one day overcome the signal-to-noise ratio problem. The most promising avenue for detecting Hawking radiation lies in the theoretical existence of primordial black holes, cosmic entities that would have formed during the earliest moments of the universe's existence. Unlike their stellar mass counterparts, these primordial black holes could possess masses ranging from microscopic to planetary scales, with the smaller specimens potentially emitting detectable levels of Hawking radiation. The physics underlying primordial black hole formation requires us to consider the extreme conditions present during the universe's inflationary epoch. In the first fraction of a second after the Big Bang, quantum fluctuations in the density of matter could have created regions sufficiently dense to collapse directly into black holes without requiring the gravitational collapse of massive stars. These formation mechanisms would have produced black holes with masses determined by the horizon size at the time of their creation, potentially yielding objects with masses far below the stellar minimum. The detection strategy for primordial black holes focuses on their final moments of existence. As these objects evaporate through Hawking radiation, they undergo a process of accelerating mass loss. The smaller the black hole becomes, the higher its temperature rises, and the more rapidly it emits radiation. In the final microseconds of a primordial black hole's existence, this process culminates in what physicists term an evaporation explosion, where the remaining mass converts to energy in a burst of gamma rays with characteristic spectral signatures. NASA's Fermi Gamma Ray Space Telescope represents our most sophisticated instrument for detecting these hypothetical evaporation events. The telescope's Large Area Telescope can identify gamma ray bursts with the specific energy signatures predicted for primordial black hole evaporation. These signatures include a characteristic spectrum of gamma rays with energies ranging from hundreds of millions to billions of electron volts, accompanied by a distinctive temporal profile that distinguishes them from other astrophysical gamma-ray sources. The search methodology involves continuous monitoring of the gamma-ray sky for transient events that match the theoretical predictions for primordial black hole evaporation. Each detected gamma-ray burst undergoes sophisticated analysis to determine whether its spectral characteristics, duration, and energy output align with the theoretical models. The challenge lies in distinguishing these hypothetical events from the numerous other sources of gamma-ray bursts, including supernovae, neutron star mergers, and active galactic nuclei. Despite decades of observation, no confirmed detection of primordial black hole evaporation has been achieved. This absence of positive results has led to increasingly stringent constraints on the abundance of primordial black holes in the universe. The lack of detection suggests either that primordial black holes are far less common than some theories predict, or that our detection methods require further refinement to identify these elusive signals. The experimental challenges of detecting Hawking radiation from actual black holes have motivated physicists to pursue an alternative approach, creating laboratory systems that mathematically replicate the conditions near a black hole's event horizon. These analog systems exploit the fundamental similarity between the mathematical descriptions of various physical phenomena, allowing researchers to study Hawking-like radiation in controlled terrestrial environments. The theoretical foundation for analog black holes emerges from the recognition that the mathematical equations governing sound waves in moving fluids bear striking resemblance to the equations describing light near black holes. This mathematical equivalence, first recognized by William Unruh in the 1980s, suggests that acoustic waves in appropriately configured fluid systems can experience phenomena analogous to Hawking radiation. The most extensively studied analog systems involve supersonic fluid flows that create acoustic event horizons. When a fluid accelerates past the speed of sound, it creates a boundary beyond which sound waves cannot propagate upstream, mathematically mimicking the light-trapping properties of a black hole's event horizon. In these systems, quantum fluctuations in the fluid should produce pairs of acoustic phonons, with one member of each pair trapped downstream while the other escapes upstream, creating an analog of Hawking radiation. Bose-Einstein condensates have emerged as particularly promising platforms for analog black hole experiments. These quantum states of matter achieved by cooling atoms to temperatures within billionths of a degree above absolute zero exhibit collective quantum behaviors that facilitate the creation of acoustic event horizons. Researchers can manipulate these condensates using laser beams to create flowing configurations that replicate the gravitational field structure near black holes. The experimental methodology involves creating a flowing Bose-Einstein condensate where the local speed of sound varies spatially, producing regions where the flow velocity exceeds the sound speed. Quantum fluctuations in this system generate correlated pairs of phonons, with detailed measurements required to detect the subtle correlations that would indicate Hawking-like radiation. The challenge lies in achieving sufficient measurement precision to distinguish the predicted signal from thermal noise and other experimental artifacts. Several research groups have reported preliminary evidence for analog Hawking radiation in various experimental systems. However, the interpretation of these results remains contentious within the scientific community. The fundamental question concerns whether the observed phenomena truly represent the quantum mechanical process underlying Hawking radiation, or whether they reflect classical effects that superficially resemble the predicted quantum signatures. The significance of successful analog experiments extends beyond mere confirmation of Hawking's predictions. These systems provide controllable platforms for investigating the fundamental physics of quantum field theory in curved space-time, potentially revealing new insights into the relationship between gravity and quantum mechanics. Moreover, they offer opportunities to explore variations and extensions of Hawking's original calculations that would be impossible to test using astrophysical black holes. The direct detection of Hawking radiation from astrophysical black holes represents perhaps the most challenging observational goal in contemporary physics. The extraordinary faintness of this radiation, combined with the overwhelming brightness of other astrophysical sources, creates a signal-to-noise problem of unprecedented difficulty. Nevertheless, the scientific community continues to pursue increasingly sophisticated detection strategies driven by the profound implications that successful observation would have for our understanding of fundamental physics. The theoretical predictions for Hawking radiation from stellar mass black holes reveal the magnitude of the detection challenge. For a black hole with 10 times the mass of our Sun, the peak wavelength of Hawking radiation lies in the radio spectrum, with a characteristic temperature of approximately 6 nanokelvins. This temperature corresponds to photons with energies roughly 1 trillion times smaller than typical radio astronomy signals, making them virtually impossible to distinguish from thermal noise in any conceivable detector. However, the situation becomes more favorable when considering black holes in extreme astrophysical environments. Black holes actively accreting material from companion stars or surrounding gas clouds emit intense radiation across the electromagnetic spectrum due to the heating of infalling matter. While this accretion radiation completely overwhelms any Hawking radiation signal, it also provides opportunities for indirect detection strategies that exploit the unique properties of Hawking radiation. One promising approach involves searching for the subtle modifications that Hawking radiation should produce in the observed spectra of accreting black holes. The quantum nature of Hawking radiation creates correlations between emitted photons that should be detectable as slight deviations from the expected thermal spectrum of accretion radiation. These correlations, known as quantum entanglement signatures, would provide unambiguous evidence for the quantum mechanical origin of the radiation. Advanced space-based observatories represent our most sophisticated tools for pursuing these detection strategies. The James Webb Space Telescope, with its unprecedented infrared sensitivity, enables observations of black hole environments with previously unattainable precision. Similarly, future X-ray missions like the proposed Athena Observatory will provide the spectral resolution necessary to identify subtle quantum signatures in black hole emission. The development of gravitational wave astronomy has opened entirely new avenues for Hawking radiation detection. The mergers of black holes detected by LIGO and Virgo create extreme conditions where quantum effects near event horizons might be amplified to detectable levels. The final moments of black hole mergers involve the formation of highly distorted event horizons that could enhance Hawking radiation emission, potentially making it observable in the gravitational wave signals. Theoretical advances in quantum gravity have also suggested novel detection strategies based on the relationship between Hawking radiation and black hole information processing. Recent developments in holographic duality and the ADS-CFT correspondence have revealed deep connections between black hole thermodynamics and quantum information theory. These insights suggest that Hawking radiation might carry subtle information signatures that could be detected using quantum error correction techniques applied to astrophysical observations. The search for Hawking radiation has also benefited from advances in quantum sensing technology. Quantum interferometers and squeezed light techniques, originally developed for gravitational wave detection, offer unprecedented sensitivity to faint electromagnetic signals. These technologies might eventually enable the detection of Hawking radiation from primordial black holes or provide the precision necessary to identify quantum signatures in astrophysical black hole observations. The absence of confirmed Hawking radiation detection after decades of searching has led to increasingly creative experimental approaches. Some researchers have proposed using the extreme environments near neutron stars as natural laboratories for studying quantum effects in strong gravitational fields. Others have suggested that dark matter interactions with black holes might amplify Hawking radiation to detectable levels, creating observable signatures in gamma-ray observations. The quest to detect Hawking radiation continues to drive technological innovation and theoretical development across multiple disciplines. Whether through direct observation of evaporating primordial black holes, successful analog experiments, or the identification of quantum signatures in astrophysical observations, the eventual detection of Hawking radiation would represent one of the most significant experimental achievements in the history of physics, validating our understanding of quantum mechanics in the most extreme environments the universe can provide. Behind every revolutionary scientific discovery lies a remarkable human story, and the tale of Hawking radiation emerges from one of the most extraordinary minds in modern physics. The magnitude of Stephen Hawking's contributions to our understanding of the universe extends far beyond his eponymous radiation, encompassing a lifetime of groundbreaking theoretical work that fundamentally altered our comprehension of cosmology, quantum mechanics, and the nature of space-time itself. The significance of examining Hawking's broader legacy becomes apparent when we consider how his unique approach to physics, characterized by an almost supernatural ability to visualize complex mathematical relationships without conventional calculations, enabled him to perceive connections that eluded his contemporaries. His methodology represented a departure from traditional computational physics, relying instead on profound geometric intuition and an extraordinary capacity for mental visualization that allowed him to navigate the most abstract realms of theoretical physics with remarkable clarity. Stephen William Hawking's journey began in Oxford on January 8, 1942, during the height of World War II. His early academic career showed promise but little indication of the revolutionary contributions that would follow. At Oxford University, he pursued physics with what he later described as deliberate mediocrity, completing his degree with minimal effort while focusing on rowing and social activities. This apparent lack of academic intensity would prove deceptive, as his true intellectual capabilities remained largely untapped during these formative years. The pivotal moment in Hawking's life arrived during his first year of graduate studies at Cambridge University in 1963. At the age of 21, he received a diagnosis that would have devastated most individuals but instead catalyzed one of the most remarkable careers in scientific history. Motor neuron disease, also known as amyotrophic lateral sclerosis or Lou Gehrig's disease, typically progresses rapidly, with most patients surviving only 2 to 5 years following diagnosis. The medical prognosis was unambiguous and grim: progressive muscle weakness, eventual paralysis, and death within a few years. However, Hawking's response to this devastating news demonstrated the extraordinary resilience that would characterize his entire career. Rather than succumbing to despair, he experienced what he later described as a profound shift in perspective. The diagnosis forced him to confront his mortality directly, leading to an intensification of his intellectual focus and a determination to contribute meaningfully to physics while time remained. This psychological transformation proved crucial, as it coincided with his deepening engagement with cosmology and general relativity. The progression of his disease followed an atypical pattern, advancing far more slowly than medical expectations suggested. This unexpected reprieve allowed Hawking to embark on a research career that would span more than 50 years, during which he would make contributions to physics that fundamentally altered our understanding of the universe. His physical limitations, rather than hindering his work, seemed to enhance his capacity for abstract thought, forcing him to develop an increasingly sophisticated ability to manipulate complex mathematical concepts through pure mental visualization. The psychological impact of his diagnosis extended beyond personal motivation to influence his scientific methodology. Unable to rely on conventional note-taking or computational approaches as his condition progressed, Hawking developed an extraordinary capacity for mental calculation and geometric visualization. This necessity transformed into a distinctive advantage, allowing him to perceive relationships and patterns in physics that might have remained hidden to researchers dependent on traditional mathematical manipulation. While Hawking radiation represents his most celebrated discovery, the breadth and depth of his contributions to theoretical physics encompass several distinct but interconnected areas of research. His doctoral dissertation, completed in 1966 under the supervision of Dennis Sciama, focused on the properties of expanding universes and marked the beginning of his lifelong engagement with cosmological problems. This early work demonstrated his ability to apply general relativity to cosmological questions with remarkable sophistication, establishing him as a rising talent in the field. The singularity theorems, developed in collaboration with Roger Penrose during the late 1960s, represent perhaps his most mathematically rigorous contribution to physics. These theorems demonstrated that under general relativity, singularities, points where the curvature of space-time becomes infinite, are not merely mathematical curiosities, but inevitable features of gravitational collapse. The implications of this work extended far beyond academic interest, suggesting that the Big Bang itself began as a singularity, and that similar singularities form at the centers of black holes. The mathematical elegance of the singularity theorems lay in their generality. Previous work had suggested that singularities might form under highly specific conditions, but the Hawking-Penrose theorems proved that they emerge under remarkably general circumstances. Any sufficiently massive object undergoing gravitational collapse will inevitably form a singularity, regardless of symmetry assumptions or other special conditions. This universality transformed our understanding of both cosmology and stellar evolution, establishing singularities as fundamental features of Einstein's theory rather than exceptional cases. Hawking's work on black hole mechanics during the early 1970s established the mathematical framework that would later enable his discovery of black hole radiation. His area theorem, proved in 1971, demonstrated that the surface area of a black hole's event horizon can never decrease, regardless of what falls into the black hole or how black holes merge. This theorem possessed profound implications for black hole physics, as it suggested a deep connection between black hole surface area and entropy, the thermodynamic quantity that measures disorder in physical systems. The mathematical proof of the area theorem required sophisticated techniques from general relativity and differential geometry. Hawking demonstrated that the expansion of the event horizon is always non-negative, meaning that black holes can only grow or remain constant in size, never shrink. This result appeared to contradict the possibility of black hole evaporation, making his later discovery of Hawking radiation all the more surprising and revolutionary. His contributions to the understanding of black hole thermodynamics, developed in collaboration with James Bardeen and Brandon Carter, established the 4 laws of black hole mechanics in direct analogy to the laws of thermodynamics. These laws reveal deep connections between gravitational physics and thermodynamics, suggesting that black holes possess temperature and entropy in ways that had never been previously recognized. The surface gravity of a black hole, analogous to temperature, remains constant across the event horizon, while the area of the event horizon, analogous to entropy, can only increase. The no-hair theorem, though not exclusively Hawking's work, received significant development and refinement through his research. This theorem states that black holes can be completely characterized by only 3 properties: mass, electric charge, and angular momentum. All other information about the matter that formed the black hole is lost, leading to the profound questions about information conservation that would later motivate much of his work on the information paradox. Hawking's influence extended far beyond the confines of academic physics through his extraordinary ability to communicate complex scientific concepts to general audiences. His approach to science communication represented a paradigm shift in how theoretical physicists engaged with the public, demonstrating that the most abstract and mathematical aspects of physics could be made accessible without sacrificing scientific accuracy or intellectual rigor. The publication of A Brief History of Time in 1988 marked a watershed moment in popular science writing. The book's success, remaining on bestseller lists for more than 4 years and selling over 10 million copies worldwide, demonstrated an unprecedented public appetite for serious scientific discourse. Hawking's writing style combined mathematical precision with accessible language, avoiding equations while maintaining conceptual accuracy. The book's impact extended beyond mere popularity, inspiring an entire generation of young people to pursue careers in physics and astronomy. The pedagogical approach employed in A Brief History of Time reflected Hawking's deep understanding of how scientific concepts develop and interconnect. Rather than presenting physics as a collection of isolated facts, he demonstrated how theories emerge from fundamental questions about the nature of reality. His discussion of the relationship between general relativity and quantum mechanics, the origin and fate of the universe, and the possibility of a unified theory provided readers with a coherent framework for understanding modern physics. His subsequent books, including The Universe in a Nutshell and The Grand Design, continued this tradition of accessible scientific communication while incorporating more recent developments in theoretical physics. These works addressed increasingly sophisticated topics, including M-theory, the multiverse hypothesis, and the role of quantum mechanics in cosmology, while maintaining the clear, engaging style that characterized his earlier writing. The broader cultural impact of Hawking's communication efforts cannot be overstated. His appearances on television programs, documentary films, and public lectures brought theoretical physics into mainstream consciousness in ways that had never been achieved previously. His distinctive computer-generated voice, necessitated by his physical condition, became instantly recognizable worldwide, symbolizing the triumph of human intellect over physical limitations. The psychological and social dimensions of Hawking's public engagement revealed important insights about the relationship between science and society. His willingness to discuss the philosophical implications of his scientific work, including questions about the existence of God, the nature of time, and the possibility of time travel, demonstrated that physics addresses fundamental questions about human existence and our place in the universe. This approach helped bridge the artificial divide between scientific and humanistic inquiry, showing that the most profound scientific discoveries have direct relevance to questions of meaning and purpose. His advocacy for space exploration and his warnings about existential risks to humanity reflected a deep sense of responsibility about the practical implications of scientific knowledge. Hawking argued that the long-term survival of human civilization depends on our ability to establish self-sustaining colonies beyond Earth, a perspective that has influenced contemporary discussions about space exploration and planetary protection. The legacy of Hawking's scientific communication extends through the countless researchers, educators, and science communicators who have adopted his approach to public engagement. His demonstration that complex scientific concepts can be made accessible without sacrificing. Rigor has influenced an entire generation of scientists to engage more actively with public education and outreach. The enduring fascination with Hawking's work reflects not only the revolutionary nature of his scientific discoveries, but also the profound human story of intellectual triumph over physical adversity. His life demonstrated that the most severe limitations can sometimes catalyze the most extraordinary achievements, transforming apparent disadvantages into unique advantages that enable unprecedented insights into the nature of reality itself. The questions that Hawking posed about the universe continue to drive contemporary research in theoretical physics, cosmology, and quantum gravity. His vision of a universe governed by comprehensible mathematical laws, yet filled with mystery and wonder, continues to inspire new generations of scientists to push the boundaries of human knowledge and understanding. We stand at the threshold of a profound realization about the nature of our universe. The journey through Hawking radiation has revealed something far more extraordinary than the simple fact that black holes can emit particles. We have uncovered a fundamental truth about reality itself, that the universe operates according to principles so elegant and interconnected that even the most seemingly impossible phenomena emerge naturally from the marriage of quantum mechanics and general relativity. The discovery of Hawking radiation represents more than just another milestone in theoretical physics. It serves as a testament to the power of human curiosity when confronted with apparent contradictions in our understanding of nature. When Stephen Hawking first calculated that black holes must emit thermal radiation, he was not merely solving an academic puzzle. He was revealing a deep connection between gravity, thermodynamics, and quantum mechanics that continues to reshape our understanding of physical reality. Consider the breathtaking scope of what we have explored together. We began with the classical conception of black holes as cosmic vacuum cleaners, objects so gravitationally powerful that nothing, not even light, could escape their grasp. This picture, while compelling and mathematically consistent within the framework of general relativity, represented only part of the story. The introduction of quantum mechanical effects near the event horizon revealed that black holes are far more dynamic and complex than classical physics suggested. The mechanism of Hawking radiation itself demonstrates the profound interconnectedness of physical phenomena. Virtual particle pairs, constantly appearing and disappearing throughout empty space, become real particles when separated by the intense gravitational field near a black hole's event horizon. This process, occurring at the intersection of quantum field theory and general relativity, shows us that the universe operates according to principles that transcend the boundaries between different areas of physics. The implications of this discovery extend far beyond black hole physics. Hawking radiation suggests that information, energy, and entropy are related in ways that challenge our most basic assumptions about the nature of physical reality. The black hole information paradox, which emerges directly from Hawking's work, has forced physicists to reconsider fundamental questions about the conservation of information in quantum mechanical systems and the relationship between microscopic and macroscopic descriptions of physical phenomena. The temperature relationship in Hawking radiation reveals another layer of cosmic irony. Smaller black holes are hotter than larger ones, meaning they radiate more intensely and evaporate more quickly. This inverse relationship between mass and temperature suggests that as black holes lose mass through radiation, they become increasingly hot and radiate even more rapidly, leading to a runaway process that culminates in explosive evaporation. The largest black holes in the universe, those supermassive giants at the centers of galaxies, are actually the coldest objects we know, with temperatures measured in billionths of a degree above absolute zero. The timescales involved in black hole evaporation boggle the human imagination. A black hole with the mass of our Sun would take approximately 10 to the power of 67 years to evaporate completely through Hawking radiation. This number is so incomprehensibly large that it makes the current age of the universe, roughly 14 billion years, seem like an infinitesimal moment. Yet this process is inevitable, suggesting that even the most massive and enduring objects in the universe are ultimately temporary phenomena. The search for experimental confirmation of Hawking radiation has pushed the boundaries of both theoretical and experimental physics. While we have yet to directly observe Hawking radiation from astronomical black holes, the development of analog systems in laboratory settings has provided compelling evidence for the underlying physics. These experiments, using sound waves in fluids or light in optical systems, create artificial event horizons that exhibit radiation patterns consistent with Hawking's predictions. The success of these analog experiments suggests that the fundamental physics underlying Hawking radiation is correct, even if direct astronomical confirmation remains elusive. The broader implications of Hawking radiation for our understanding of the universe are profound and far-reaching. If black holes can evaporate completely, what does this mean for the ultimate fate of the universe? In the far-distant future, when all stars have burned out and all ordinary matter has been consumed by black holes, these black holes themselves will slowly evaporate through Hawking radiation. The universe may end not with a bang or a whimper, but with the faint glow of the last evaporating black holes, returning their energy to the cosmic void from which they came. The resolution of the black hole information paradox, currently one of the most active areas of research in theoretical physics, may require revolutionary new insights into the nature of space-time itself. Recent developments in string theory, loop quantum gravity, and other approaches to quantum gravity suggest that information may indeed be preserved in Hawking radiation, but in ways that require us to fundamentally reconsider our understanding of space and time at the smallest scales. The holographic principle, which emerged partly from studies of black hole thermodynamics, suggests that all the information contained within a volume of space can be encoded on its boundary. This principle, if correct, would represent a revolutionary new understanding of the relationship between information and space-time, with implications that extend far beyond black hole physics to encompass the entire structure of physical reality. Stephen Hawking's legacy extends beyond his specific scientific discoveries to encompass a broader transformation in how we think about the universe and our place within it. His work demonstrated that the most abstract mathematical theories can have profound implications for our understanding of physical reality. The techniques developed to understand black hole physics have found applications in diverse areas of physics, from condensed matter systems to cosmology. The philosophical implications of Hawking radiation cannot be ignored. If the universe is fundamentally quantum mechanical in nature, and if information is truly conserved in all physical processes, then the evaporation of black holes through Hawking radiation represents a cosmic recycling process in which information is never truly lost, only transformed. This perspective suggests a universe that is both more strange and more beautiful than our everyday experience suggests. The continuing search for a complete theory of quantum gravity, motivated in large part by the puzzles raised by Hawking radiation, represents one of the most ambitious intellectual endeavors in human history. The successful unification of general relativity and quantum mechanics would represent a triumph of human reasoning comparable to the greatest achievements in the history of science. The insights gained from studying black hole physics suggest that this unification may require us to abandon some of our most cherished assumptions about the nature of space, time, and causality. The story of Hawking radiation ultimately reveals the power of human curiosity and imagination when confronted with the deepest mysteries of existence. Stephen Hawking's willingness to follow mathematical logic wherever it led, even when it challenged conventional wisdom, exemplifies the scientific method at its finest. His discovery that black holes are not perfectly black but emit thermal radiation represents a triumph of theoretical reasoning that continues to inspire new generations of physicists and astronomers. As we look toward the future, the implications of Hawking radiation continue to unfold. Advanced gravitational wave detectors may eventually provide indirect evidence for Hawking radiation through precise measurements of black hole mergers. Proposed space-based telescopes designed to detect the gamma-ray signatures of evaporating primordial black holes may finally provide direct observational confirmation of Hawking's predictions. The development of quantum computers and other advanced technologies may enable more sophisticated simulations of black hole physics, providing new insights into the fundamental nature of space-time. The legacy of Hawking radiation extends beyond physics to encompass our broader understanding of the universe and our place within it. This discovery reminds us that the universe is far stranger and more wonderful than our everyday experience suggests. It challenges us to think beyond the obvious and to embrace the counterintuitive insights that emerge from careful mathematical reasoning. Most importantly, it demonstrates that the human capacity for understanding has no apparent limits, that even the most exotic and extreme phenomena in the universe can yield their secrets to patient and persistent inquiry. The enigma of Hawking radiation, therefore, is not merely a puzzle to be solved, but a window into the deepest mysteries of existence. It reveals a universe that is simultaneously comprehensible and mysterious, governed by mathematical laws yet filled with phenomena that challenge our most basic assumptions about reality. As we continue to explore these mysteries, we carry forward Stephen Hawking's vision of a universe that can be understood through the power of human reason, creativity, and imagination. The radiation that bears his name will continue to illuminate the cosmos long after the last star has burned out, a fitting monument to one of the greatest minds in the history of science.